So we're going to dive right in and talk about Chapter 8. Chapter 8 is about rotational dynamics, and the primary thing that we're going to talk about is going to be torque. Torque tau is equal to generally R times F, radius times a force. So this is kind of a rotational analog to force. It is a rotational force. And the clearest example I can think of to demonstrate torque that you use every single day is a door. A door has a hinge, and a door, and a doorknob. In order to make this door rotate, I have to apply some force to it. I usually apply force F at some distance away from this hinge, some distance R. So the rotational force that it takes to open this door, tau, is equal to R times F, where R is distance from an axis of rotation. In this case, for a door, the axis of rotation is the hinge. Hinge equals axis. And then F is how hard I push on the door, the force that I apply, how hard I push. We can show in class where, depending on where I push on the door, determines how much force I have to apply. The minimum force that I need to apply is going to occur at the maximum radius, because tau is equal to R times F. For opening a door, tau remains constant at some minimum value, as some minimum constant, some minimum amount that I have to push on the door to open. So in general, if R decreases, then F has to increase to compensate. So what does that mean? If R decreases, let's say instead of pushing where I'm supposed to at my force F, let's say I decrease my R. Let's say I try to open the door from right in the middle of it. Now you will see this happen. You can do this experiment yourself. But to open the door from the middle instead of the doorknob, I have to apply a much bigger force because I have to reach this minimum torque. My R is too small to give me a decent value to contribute towards this torque, so my force has to correspondingly increase. We have some conventions with torque. If something is being caused to rotate clockwise, so if I'm going clockwise, then my torque is negative. If I'm going counterclockwise, then the torque is positive. But what? I have my door. There's my hinge. Here's my door. Here's my doorknob. Let's say I don't push directly on it. Let's say I push at some angle F. Some force F. What actually is happening here? How can I rewrite my torque? Now, I'm trying to make the door swing this door swing in this direction. So I'm trying to make the door basically from the direction I'm pushing on it, I'm trying to make it swing up and over, up and out around this axis of rotation. So I can take my force, which I see is at some angle, and I can break it up. as we've done with anything that is ever at an angle throughout this entire class, I can break this force up into two different pieces. I have some force in the x direction, I have some force in the y direction. So Fx, Fy, and then my hypotenuse is going to be my F. So which of these two forces, my Fx, which if I push on the door would push it horizontally, or my Fy is actually contributing to opening the door? If we look closely, we can obviously see that I want my door to swing open and out, so the force that applies to that is going to be my Fy. So I can use my trigonometry to figure out that Fy is equal to F times sine of theta. So the torque that actually makes this door rotate, if your force is applied at an angle, is going to be R times Fy. Again, if I look at where the forces are acting, Fx is acting entirely horizontally. If I push in the Fx direction, nothing's going to happen to this door. This door is going to move horizontally. It's not going to open. The only way I can make this door open is to push Fy, to push the door forward. And then it rotates around its axis of rotation. So Fy is the force that actually is responsible for giving me a torque. And now I know torque R is equal to Rfy is equal to R times F times sine of theta. And this right here is going to be the most general definition for torque. The direction of torque is going to come, again, from this right-hand rule. So we need to see this in class. I'll need to demonstrate it for you so you can kind of get an idea of what it's like. But what the right-hand rule does. Direction from the right-hand rule. Right-hand rule. I take my fingers and point them in the direction of R, of my radius. My fingers curl in the direction of F. And then my thumb points in the direction of torque. And this is going to be something that's very, very difficult to draw. Try. Here's my door. Here's my doorknob. Here's my distance R. So going from my hinge to the place where I apply my force, from my hinge to my force, I'm going to be going this way. So my fingers are going to point this way. And then the force that I apply to open the door is going to be pointed up. So my fingers are going to curl up. Curl up. And my thumb, in this case, points out. And we'll need to practice with this in person. It's very hard to draw on an iPad screen. So moving on a little bit more, let's move forward. Now what happens when we have forces acting in equilibrium? It's just a very quick little thing to note that your book kind of glosses over a little bit. In equilibrium, the sum of forces acting on some object is equal to 0. Similarly, for torque, for things rotating, the sum of torques acting on an object in equilibrium is also equal to 0. So let's break torque down a little bit more. Torque is really just an angular force. It's a force acting at an angle. So we can fiddle with this a little bit, because we know a little bit about angular forces already. And we know about forces in general. So here's some little ball that I'm swinging around in a circle that has some rotational force that I'm applying to it. That force is kind of like a tangent force, because it's being applied to make this thing move in a circle. It's being applied tangent to that circle. And the tangent force that I get is equal to the mass times the tangent acceleration. So the torque that this tangent ball circle feels is equal to the tangent force times r. Torque is equal to r times f. So it depends on the force that I'm applying and the distance I am from the center of my circle. Now I can just plug in Ft equals mat. So I can get my tau is equal to m times at times r. If I'm trying to get this into angular terms, since torque is acting at angles, it's kind of a circular analog to force, then I need to remember that at, the tangent acceleration, is equal to r times alpha, something we learned in chapter 7. So now I can plug this in, and I will find that the torque is equal to m times r alpha, where I'm plugging in for the tangent acceleration, times r. So now I find that torque is equal to m, I'm going to combine my r's to get r squared, times alpha. This looks similar to F is equal to m times a. Torque is the rotational analog to force. Alpha is the rotational analog to a, which means mr squared is going to be the rotational analog to m. And mr squared has a very specific definition. I equals mr squared, where I is something called the moment of inertia. So if you remember, Newton's second law says the sum of forces is equal to mass times acceleration. We can do an analogy to the force, the sum of torques is equal to I times alpha. We hear I is going to be equal to the most general definition, sum of mr squared. So this I, the moment of inertia, is a rotational analog to mass, and we can see that when you're rotating in circles, your moment of inertia depends not just on your mass, on the mass, and depends on r, or how that mass is actually distributed. Usually what we need to do is use calculus to get these moments of inertia. You'll have a handy-dandy table from your book that you can use to calculate these without using actual calculus. So to summarize, I equals moment of inertia. It's a lot like the mass for a rotating object. It depends on the object's mass, its shape, or how that mass is distributed. and also the axis that the mass rotates around. We'll do an example in class to demonstrate this. So when you're thinking a moment in inertia, think about ice skating. And we'll talk about what that means in class. We've got more things we can do with rotating objects. Rotating objects, since they're rotating, since they're moving, they have some energy. They have some rotational kinetic energy. And we can derive an equation for this from our general equation. Kinetic energy is equal to 1/2 times m times v squared. Let's say I have a circle. That circle's rotating. I can take the kinetic energy of all the little points on that circle. Each little point. So it's kind of like I have a bicycle tire and I'm looking at all my spokes and my kinetic energy of each one of these little points. So I can actually sum up all the kinetic energy that I have in my circle. But I'm rotating in a circle, so I want to use, instead of v, I want to use rotational velocity. So kinetic energy is going to be equal to the sum of 1/2 times m, and instead of v, I'm going to plug in the rotational analog to v, r times omega, to get that rotational velocity in there, that omega. We remember that v is equal to r omega from chapter 7. So now kinetic energy is equal to sum of 1/2 times m times r squared times omega. If you remember what mr squared is, kinetic energy is equal to the sum of 1/2 mr squared is the rotational analog to mass, I, and omega is the rotational analog to velocity, 1/2 I omega squared. Kinetic energy of a rotating object. Almost exactly the same as an object that's just moving in a straight line. We just need to replace with the rotating analogs. This also works for momentum. We won't go into detail on deriving this equation. P equals m times v. If I want to do just the straight up analogy, my momentum, for a rotating object, we call it angular momentum, and it's equal to L is equal to rotational mass, which is I, moment of inertia, times rotational velocity, omega. L equals I omega. Or, if I want to draw analogy to my other definition from the calculus definition, if we remember, P is equal to a force times a change in time. So instead of using force, we use rotational force, tau, and change in time. Time does not depend on where you're going in a circle or not, so L can also be equal to torque times change in time. The final point to make for rotating forces, for rotational dynamics, is something called the conservation of angular momentum. So just like linear momentum, regular momentum in straight lines is conserved, angular momentum is conserved. It's conserved in a very specific situation if you have conservative forces acting. So if you have conservative forces acting, then the sum of forces acting are equal to 0. If you have conservative forces acting in rotational dynamics, then the sum of torques has to be equal to 0. So there's no external forces acting, so angular momentum, L, is conserved. Which means that L initially is equal to L finally. We'll do an example in class to show this as well. So for this example, you'll also want to think of the ice skater. And that is chapter 8.